So this is probably my least favorite lesson in all of calculus. Oh, maybe that's not a great way to start a lesson. So here's a super fun lesson. Yeah, you can tell I'm lying. What we're looking at today is the derivatives and integrals of inverse trig functions. And I just have a hard time getting behind these inverse trig function derivatives just because there are applications to them, but we don't really focus on them in Calc 1 at least. So the fact that typically I have students try to memorize these, and it like hurts my heart that they do. But if they show up on the AP test, I want them to have them memorized. But there's not a whole lot of application that we would do in Calc 1. Anywho, for you all, I would pause the video, write them down, have them handy if you were taking the AP test, but basically we're just going to follow whatever it says for the derivative. So no memorizing here, but just being able to follow it. So if we have the derivative of arcsine of some function, we would just say that it equals the derivative of that function over the square root of 1 minus that function squared. So just being able to follow it is what we're going to attempt to do. So for our first example, we're looking at taking the derivative of arcsine of x squared. So just looking at our derivative over here, identifying that my u in this situation is x squared. And then I'm just going to be following that my derivative of x squared is 2x. And then I'm going to have the square root of 1 minus x squared squared, so x to the 4th. Woo woo! For example 2, at least we have a little product rule to make things more interesting, but I'm going to have the derivative of x squared times the arctangent of 5x plus x squared times the derivative of this arctangent of 5x. So since my u is 5x, I'm just going to have my u prime, so 5, in the numerator. And then in the denominator, I've got 1 plus my 5x squared. And make sure that the whole thing is squared, so either put it in parentheses and say 5x all squared, or you could say 25x squared would be fine as well. But we're just going to leave it like that. For integrating, these are all set up really well for U-Substitution, where I'm looking, once I've done my U-Substitution, I'm looking to have it look exactly like this, where my u prime is actually the du, with one exception. So for our integrals, instead of having a 1 in all of these places, we could have a different number that's squared. So before we look at these, we're going to go ahead and let us have a new variable a that's greater than 0. And let's talk about the integral of 1 over the square root of a squared minus u squared. So notice that it looks like this derivative of arcsine, where we've got the u squared, we've got the radical, we've got subtraction. Instead of the 1, we're going to have a squared. And then instead of having the u prime, we've got du, which is really the same thing. So if we're taking the antiderivative here, we're going to end up with arcsine. But because we didn't have a 1 there, we had an a squared instead, we're going to have a u over a plus c. So if that a did happen to be 1, then this would be u. But if it doesn't happen to be 1, then it's not going to be u. And we'll look at some examples here in a minute. They're all going to work out this way. So another example, if you had 1 over a squared plus u squared du, notice that the tangent and cotangent are the only ones that don't have radicals in them. So I'm looking at arctangent because it was the positive version, and I've got that a squared instead of 1, that's okay, and then my plus u squared, and I've got my du for my u prime. So it's looking exactly like arctangent. Where were we? We were deciding that this was going to be arctangent, and same situation as with arcsine, we're going to have that u over a plus c. Well, we're also going to have a 1 over a out front. That happens with tangent. Let's look at one more. I want to see what happens with these absolute values of u. So let's look at the example 1 over u radical u squared minus a squared. So it does have that u on the outside. We only have two functions here that have the u outside of the radical in the denominator. So we're looking at arc cosecant or arc secant. The only difference here is that arc secant is positive. So we're going to be talking about arc secant. It's okay that it's not an absolute value here. That will come into play, but we'll see that when we take the integral. And then again, having that a squared instead of the 1 squared. That happens with the integrals. Okay, so this is going to end up being arc secant. We're going to have our u over a like these other two, but the u is going to be an absolute value. And then we're also going to have the 1 over a out front like we did with arc tangent. Something that's nice with these is that I actually just need these three written down, because if I do get something that looks like the derivative of arc cosine, it's just the negative version of the derivative of arc sine. So I would just need to multiply it by a negative over a negative, and then now I've got something that looks like arc sine. Same thing with arc tangent and arc cotangent. They're just negative versions of each other, and arc cosecant and arc secant. So these are the only three that I need written down. So for example 1, I first want to decide just which inverse trig function this is associated with. And just noticing it has the radical in it, and it also has a function outside of that radical. So I'm looking at arc secant because it has both of those things, and it's the only one of these that has a radical and something on the outside. I'm going to go ahead and use U-substitution. I'm going to choose what my u needs to be in this situation. So if I have this u squared on the inside, and I can reconcile this later, but I want to go ahead and make sure that this is happening correctly. So since I have u squared, that means that u had to be x squared, because x squared squared is x to the fourth. So if my u is x squared, my du is a 2x dx. And I am missing that 2x. So I'm going to multiply the top and the bottom of this by a 2x over 2x. That is going to give me that x squared that I needed in the denominator. So I'm going to arrange this in a way that's easiest for me to see. I want that 2x dx to be in the numerator over there. So I've got my 2x, my dx. And then I want my other x to be multiplied by the x to have my x squared on the outside, but I'm going to leave the other two out there. And then I've got my square root of, I'm going to go and write this as an x squared squared. And then I'm going to write my 4 as 2 squared, because remember it is going to have to be in that form where I have some number squared, and so that some number is 2. Sorry, I kind of wrote it a little squishy. So when we use U-substitution here, I can go ahead and replace my x squareds with u. So I'm going to have a u square root of u squared. Minus, if we want to go ahead and write this as a to the second, we can, or you can keep it as 2, it really doesn't matter. And then my numerator and my dx all get absorbed into the du. So now when I'm taking the integral, I'm following exactly what this does. I've got my u on the outside, my radical u squared minus a squared. And so now I can go ahead and take the integral, and I'm going to have that 1/2 on the outside of all of it. So I've got my 1/2 1 over a arc secant absolute value of u over a plus c. And then I just want to replace my a and my u with what they were. So my a was a 2. My u was an x squared. And then a few things that you could clean up if you wanted to. We could definitely drop the absolute value here because x squared is always going to be positive. So absolute value is not really doing anything. I could multiply my 1/2 and 1/2 if I wanted to. That's pretty much the gist. Example 2 is going to be similar, so first deciding that since this does not have a radical in it, my inverse trig function that's going to go with this is arctangent. So we can start to recognize my a squared, my u squared, but I do want to go ahead and use U-Substitution because I want to make sure that that du ends up being there. Otherwise it's going to throw me off. So I'm going to go ahead and make my u, remember this has to be that u squared. So if I take the square root of that, that's a good way to get my u. So it'd have to be a 3x because that squared is going to be 9x squared, which makes my du a 3 dx. So I actually already have a 3 here, but I have 3 times 4. So I want to go ahead and factor out a 4 so that I have just my 3 in the numerator. Like I did on the other ones, I'm going to go ahead and rewrite this as 2 squared plus 3x squared. And that way, when I go ahead and go to use U-Substitution, it's very clear that this 3dx is all the du. And then here's my a squared plus my u squared. So I'll have my 4 on the outside, but then for my integral, I'm going to have 1 over a arctangent of u over a plus c. So plugging back in what my a value is and what my u is, my a was a 2, so I've got 4 divided by 2 here. And then my u was 3x over 2 plus c. For our last example, we're going to need a little bit more manipulating before we can take the integral. So notice on this one that I don't just have one function squared and then minus a number squared or a number squared minus a function squared, because this all has x in it. I don't have anything quantity squared. So before I can actually integrate here, I'm going to need to complete the square. So reminding us how completing the square works, if you have, let's say we have an x squared plus 10x, and we're wanting this in a form where you've got something quantity squared, which is what we're about to do. Remember that you would take that b value, divide it by 2, and square it. So in this case, if I divide 10 by 2 and get 5 and then square it, that tells me that I need to complete the square with 25. Of course, I'm not just allowed to add 25 to any equation that I want, so I'm also going to subtract 25 so that it's like I'm adding 0 to it. And then with this piece right here, I'm going to be able to factor that into something quantity squared. So for this one, it would be an x plus 5 quantity squared minus 25, and notice that this is going to be a perfect square. So for the problem that we're about to look at, I could go ahead and write that 25 as 5 squared, and now I've got a function squared minus a number squared, which is exactly what we need. So going back to example 3, I'm looking at completing the square with the denominator. Sorry, what's underneath radical and the denominator? You definitely don't want that radical involved. I'm adding something in and subtracting something out, but I do have an issue with this negative on the outside of the x squared. I want to go ahead and factor out the negative. So we're going to have a positive 4x, adding something, subtracting something. So we're taking that b value, dividing by 2, and squaring it, which is going to give us 4. So I'm adding in a 4, subtracting out a 4. But because I have this negative factored out, you have to be a little bit careful here. I can go ahead and factor this piece. So I'm going to have a negative x plus 2 squared. But then for this negative 4, I don't want it to be inside the parentheses. That doesn't make any sense. So I'm going to go ahead and distribute the negative, all the positive 4 on the outside, or how I really need it to be for my inverse trig functions. Since they're underneath the radical and there's not something on the outside, I want it to look like this number squared minus function squared underneath that radical. So I'm going to go ahead and switch these when I rewrite it and say that this is the same as 4 minus x plus 2 squared. And now I have it in this form where I have the square root of a number squared minus a function squared. Okay, so now I'm going to go ahead and say, I kind of have this in the way, but we're going to go ahead and say that our u is this x plus 2, which makes du just dx. I shouldn't even have a dx. So that's not really going to change a whole lot of what we're looking at, aside from just replacing this x plus 2 with a u so that I can see that it looks like that. My du was just 1 dx. And then if I want to rewrite my 4 as a 2 squared or as a squared, I could do that. But now I've got it looking exactly like arcsine. So I'm going to have that the derivative, or sorry, the integral is arcsine u over a plus c, which when we plug back in our a and our u is going to be the arcsine of x plus 2 over 2 plus c. There are other values of a, by the way. I don't know how they all ended up being 2 for all 3 examples, but I don't know. Conspiracy.